This is Professor Thompson. I'm going to do some examples from 2.3, and the first one is number 2, and all of these examples, they just say differentiate the function. So here, f of x is pi squared, and it's tempting to use the power rule, but pi squared is just a number. Pi is 3.14, and the square of that is maybe about 10, and so this is just a function that's constantly that value. It's a horizontal line with 0 slope. So the derivative is just always 0. The next example is 14. So this is y equals x to the 5/3 minus x to the 2/3. And because they have y notation, I'm going to write dy dx, not f prime. And now I'm going to use the power rule. So this is 5/3 times x to the 5/3 minus 1, which I'll simplify in a minute. And then I subtract 2/3 times x to the 2/3 minus 1. I'm able to do those derivatives separately because of the sum and difference rule. And now to simplify those, well, 1 is 3/3, so 5/3 minus 3/3 is 2/3. And then for the second exponent, 2/3 minus 3/3 is minus 1/3. There's no need to write that in different notation or try to simplify it. Unless I specifically ask you, I'm never going to require you to simplify your derivatives unless you are given that you should in the problem. The next example is 18, and this is big S of big R, is 4 pi r squared. And remember, 4 pi is a constant, so now we're going to use what's called the constant multiple rule, which means that I just kind of leave the 4 pi there when I'm doing S prime, and I do the derivative of r squared because r is the independent variable. And so I use the power rule to get 2r, and then I can simplify that as 8 pi r. So the constant multiple rule says just leave the constants there, do the derivative with the power rule for r, and then multiply. The next example is 24. And to do 24, we have y equals sine theta over 2 plus c over theta. Well, first I'm going to simplify this before I even try to take the derivative. I don't like the fractions, so I'm just going to write 1/2 times sine theta, and then c theta to the minus 1. So here theta is the variable and c is a constant. So I'm going to write dy d theta because theta is the independent variable, and I leave the 1/2, and the derivative of sine is cosine theta. And now c is a constant, and I use the power rule on theta to the minus 1. And it works just the same way for negative exponents. It's minus 1 times theta to the minus 1 minus 1. I lower the power by 1. So to simplify that, I have 1/2 cosine theta minus c theta to the minus 2. So I know a minute ago I said not to simplify. That was me just cleaning up the problem. I would never expect for your own sake that you would write minus 1 minus 1. So I just wanted to clean up the previous line. But this is a perfectly acceptable final answer here. The next example I'll do is 26. And this is u equals the cubed root of t squared plus 2 square root of t cubed. So to do these exponents where I have a root and a power, I need to think about these as a power to a power. So this is t to the 2 to the 1/3 plus 2 t to the 3rd to the 1/2. And now a power to a power means you multiply. So this is t to the 2/3 plus t to the 3/2 times 2. And I haven't done anything with the derivative yet. I've just been rewriting the expression in a way that lets me take the derivative, because now I can use the power rule. So du dt in this case is 2/3 times t to the minus 1/3, and then I add 2 times 3/2 t to the 1/2. So both those new exponents were from subtracting 1 from the old exponent. So I had 2/3 minus 1 is minus 1/3, and 3/2 minus 1 is 1/2. And just to do a little bit of simplification, this is 2/3 t to the minus 1/3 plus 3 t to the 1/2. All right.